When you think about the interaction between charged particles in a system, we normally think about we start thinking about the Coulomb interaction. And this is natural because Coulomb interaction for a particle that is, let's say, in a system like this, it's a three-dimensional system that is uniform and isotropic. Then the interaction, the potential that is generated by the charged particle in the space surrounding it, let's say to a point with a distance r here, that interaction potential should be something like is the solution for Poisson's equation. That in this case can be written, let's say, like Laplacian of the potential is equal to 4 pi multiplied by the charge and the density, that here I'm going to write it like a delta function in the origin. Okay, so if you have this system with an epsilon here, that would be, let's say that I'm going to put an epsilon here that multiplies the epsilon 0, so that this is just a number. For silicon, for example, this is going to be around 10 times epsilon 0, so this is going to be around 10. So the solution for this equation, if this epsilon is constant everywhere, is just the Coulomb, it's just a Coulomb interaction. So phi is proportional to the charge and to epsilon and epsilon 0 and the modulus of the distance to the charge, right, which is in the origin in this case. So this would be the potential that we call Coulomb interaction, or Coulomb interaction potential, and this is the solution for Poisson equation in this case. But then a few years ago, maybe 10 years ago, there was some increasing interest in a different situation where you have an epsilon that is not constant in space. So 10 years ago, we started to investigate more this, what we call the 2D materials, like transition metal dichalcogenides, for example, and black phosphorus. These kind of materials, they are slabs, very thin slabs of a material. Many of them are semiconductors. And these materials, they have an epsilon in the bulk form that would be different from epsilon 0, of course. And then now if I have a slab like that, along the z direction, I could have a function epsilon of z that could have some value like in the bottom. Maybe it's simply the vacuum in the bottom and vacuum on the top. So I would have epsilon z equal to 1 in the bottom or in top. But in the slab, I could have some kind of epsilon of the slab that is non-zero. And now this is the one that I would put in Poisson's equation if I want to solve it. But what I'm saying now is that the actual epsilon of this system is no longer uniform. So the solution can no longer be Coulomb interaction for two charges in the system. So let's say that I put an electron and a hole in this semiconductor, for example, and I want to see a binding state, a bound state of these two things. That would be an exciton, for example. So this bound state would be like in principle, like a 2D hydrogen atom. But it may be that it's not exactly a hydrogen atom because the interaction should not be a Coulomb interaction. So strictly speaking, it's not really like a 2D hydrogen atom exactly. So you can also think about this thing like if you have a 2D system like that, then you have like electric field lines connecting these two charged particles. Some of the lines would go above the layer, some of them will go below the layer, and because of that they would feel the system in a different way. So if the charges are very far from each other, then you would be in a strictly two-dimensional plane with all the electric field lines going out of the system. But now, like out of the slab. But if they are very close to each other, maybe most of the lines would be inside the material, then it should look like a Coulomb interaction again. So what I'm saying is, depending on the distance between between the charges, it can be that the interaction is more close to what you would expect from a Coulomb interaction or not. That affects a lot the results that you see in 2D materials, for example. So as I said, this kind of pair, electrons and holes, they are called excitons, and it's possible to find the exciton binding energy. It's possible to see that like with photoluminescence or absorption experiments. And when they do that, there are already reports about that. I will put all the reports that I'm talking about, I will put all the references here in the description of this video. So when you look at these energies, if the system is strictly three-dimensional, like in a bulk material, not in a slab like that, these energies, they are indeed proportional to a kind of a effective Rydberg energy divided by n squared. And you can check that experimentally. If you put excitons in a three-dimensional material, like a bulk material, then you would see that the exciton energies, they all follow a Rydberg series like that, but of course with an effective Rydberg energy, because they really look like an hydrogen atom. The problem is, in this case, it's not really a three-dimensional hydrogen atom, it should be like a 2D hydrogen atom. So let's solve again Schrödinger's equation for a 2D system, like an in-plane Coulomb interaction between two charges, and then you solve Schrödinger equation in 2 dimensions. You would get something like this, n minus 1/2 squared. So the Rydberg series for the hydrogen in 2 dimensions should look like that. But the problem is, when they do the experiment with TMDs and black phosphorus, as I said here, that's not what they see. So this was very puzzling, but there was a paper a few years ago that discussed this thing. They found that the series doesn't look like a hydrogenic system or a hydrogenic series, as you would expect. But then they claim that this comes from the fact that the potential is not a Coulomb potential. So you cannot solve Schrödinger equation for Coulomb potential and find the energies like that. So you would find this expression if you do Coulomb interaction in 2D. But the point is, Coulomb interaction is only if epsilon is constant everywhere. But it's not in this case. So what I have to do is to solve again Poisson equation, taking into account that the epsilon depends on z, so it should be rewritten this way, right? So epsilon of z, then I have this multiplied by with a dot like that, and then I have 4 pi delta charge and this epsilon 0, and that should be the way to write it. So now I have this thing here that doesn't look like a Poisson equation, the normal Poisson equation that you have that generates the Coulomb interaction, and you have to solve it again. It's not going to give you something like that. It's going to give you something else. Okay. So what we are going to do now in this video is to develop or to solve this Poisson equation in this way, where you have this epsilon that depends on z, and it has like 3 different values along the z direction. So actually, then when you solve this thing, you get another kind of potential that it has been discussed in this previous paper that I just mentioned, and it was like there was a study for different two charges interacting in a 2D material. That was in 1979 paper by Keldysh, and then there is a discussion of how the potential should be modified by the fact that you have an epsilon that depends on z. So for many years, and like until a few years ago, we always call this interaction between charges in the plane as a Keldysh interaction. So we would say like, okay, like if you have a bulk material, then the interaction is Coulomb, but if it is a 2D system, then it's a Keldysh interaction, which is like the 2D version of a Coulomb interaction. But then a few years ago, there was a paper that was released in arXiv, which is a translation of a paper from 1967, so more than 10 years before the Keldysh work. This was a paper written by Natalia Rytova, and it was translated by Alexei Chernikov and Misha Glazov, and now it's in arXiv. And it has more or less the same description as Keldysh did, but then it was like in Russia until a few years ago, and now it's translated. Now we know that there was like this former paper also discussing this interaction between charges in a 2D system where epsilon depends on z. So that's why right now when we talk about this interaction between charges in a 2D material, we say that they are interacting via Rytova-Keldysh potential. And this is what I'm going to develop here in this video. How does this Rytova-Keldysh potential look like? It doesn't look like that. That's the point. So there is something else that they call Keldysh potential, because it has the mathematically the same expression too, and but it's in a different context, which is when you have a charge and you have screening due to other charges in the system. So it's a many body problem. Then you can solve it, and you see that the screening of extra charges also leads to a Keldysh potential, but that's not the one that we are going to discuss here. The one I'm going to discuss here is for a single particle problem. You have a single particle in a system where epsilon depends on z, so the interaction is no longer Coulomb interaction. It's what I'm going to present now. So we start with an approach that I saw in a paper by Pierluigi Cudazzo and some other co-workers. I'll put the references here in the description of this video. But in that description, it's a very simple way of finding this Keldysh potential, or showing how this thing is different. So the idea is you have an infinitely thin slab, and then you have Poisson equation, and then I will write it like this. As it is infinitely thin, I'm going to write it like this. So I have minus 4 pi, I'm putting an electron here, and then delta of r minus r0. And so this r0 here, I'm going to put it here so that I put in the plane, I'm going to use the origin as 0. The charge is in the origin, I mean. But the charge in z direction, I'll put it in the plane. It's going to be in z0. And I will explain a little bit later why I prefer to do it like that. So here, I'm not saying that I have different epsilons, but I'm going to add a consequence of having different epsilons. The consequence is I have extra charges here, or extra fields that come from polarizability of the system here. So there should be an extra induced charge. That's what I mean. In this case, this would be something like a potential that would depend on this, on the divergence of the polarization, and this is what was caused by this environment around the plane. Okay. And this is going to be like, this P is going to be in the plane, of course, but then I have a delta of z minus z0, so that this thing happens only in the plane. And this polarization, I'm going to say that it is proportional to, let's say, I'll call it alpha 2d, and it's proportional to the, so this is just the polarization. Sorry about that. Just this thing here. This thing will be proportional to nabla of the potential itself. So then what I'm going to rewrite here is something like 4 pi e delta of r minus r0 and minus 4 pi alpha 2d, and this is going to become Laplacian, but only the in-plane coordinates of phi, although this is still a function of r and z, like let's say rho and z. So that you have like a z direction and an in-plane direction too, but it's multiplied by z minus delta of z minus z0. Okay, now to solve this equation, I'm going to take a Fourier transform of everything. So the left hand side of the equation is going to become minus then in-plane k vector squared plus kz squared and phi. And now this phi is of k in the plane and kz. So when I write k here, it's going to be only in plane coordinates. Okay. So now I take the Fourier transform of this delta here. It's going to become minus 4 pi e, and then the Fourier transform of this delta is going to give me something like exponential of I kz z0. And because this r0, it's 0 for x and y coordinates, but z0 for z coordinate, okay? And for the other part here, I will take the 4 pi alpha, this is all constant, but Fourier transform of the in-plane coordinates here will give me an extra k squared here, and a phi of k, and then as this is Fourier transform of a delta function in z0, this will give me z0 here, and exponential of I kz z0. And here's what I said, that you need to put a z0 here. Although if you look at the paper there, you wouldn't see this, but I prefer to write it in this way, because then it becomes explicitly that you have a kz dependence in the left side of the equation, and if this z0 is 0, then you will put this thing to 1 and this thing to 1, and then it becomes unclear where the kz dependence is in the right hand side of the equation. That's why I wrote it like that. Although I mean it's just a different way of writing, but it's the same as in the paper there. Okay. So also when I made the Fourier transform here, there was a plus sign here. So now I'm going to cancel these signs, and it will be like this, and now here I will have a minus sign again. Okay, so I will now isolate this phi of kz, of k and kz, and now this is going to be isolated like there is this exponential, and then in the denominator I have k squared plus kz squared, and then these multiply all the rest here, which is all constant, right? 4 pi e and minus 4 pi alpha 2d, and here I have k squared and this phi of k and z0. Now I take the Fourier transform back to the z direction here, and then I have like Fourier transform, inverse Fourier transform for the z direction for phi of k and k0 and kz. And once I take this Fourier transform, I will take the solution exactly at z0 again. Okay, so because I'm going to bring this phi back to the z direction. I already made this here, right? So I don't need to do anything in this part of the equation anymore. So all these things here, they are all constant. 4 pi e, 4 pi alpha, and then I have this phi of k and z0, right? And then now what I really need to take a Fourier transform or inverse Fourier transform, it needs to be something like dkz of e to the I kz z0 and this denominator. Okay, so now there is something to be discussed here, which is there is a way to solve this thing analytically, this interaction, this integral analytically, but sorry, it's a Fourier transform. There is something else in the argument here, so it should be something like z minus z0 actually. Okay, so then and this is a minus here. Okay, so then this integral here, I don't have a form for it in the way that it is, but I know that there is an integral there is an inverse Fourier transform that is easy to find, which is Fourier transform of, let's write it in the direct Fourier transform. The Fourier transform of this equation e to the minus a modulus of x, that would be 2a over a squared plus k squared. So then with this expression here, I can find what I have, something similar to what I have in this integral here. But to make it close to what I get here, I would need to put like a 2 modulus of k on top and the bottom, so that I don't change the result here. And then that's it. Now it looks like what I have here. There is this 2a and an a squared here. You see 2k and a k squared here in the bottom. So this will allow me to rewrite this equation in a more in an analytical form, analytical solution for z direction. So in the end I will get something like phi of k and z. And now I'm going to put it in z0, right? So this is going to be something like 4 pi e minus 4 pi alpha and that k squared and phi of k and z0. So I already put this in z0 here, as I said I would. So after the integral here, I would get something like e to the minus k in modulus multiplied by z minus z0. But then this z minus z0, that would be in modulus too. So that z minus z0 is equal to 0, because I'm choosing z equal to 0. So this thing will be 1. So I don't need to worry about this. But in the bottom here, I will have to put an extra term like 2 modulus of k, right? So now I can cancel these two in different parts here. There will be a 2 here and a 2 here. And now here it is also 1 over k. And I will put this 1 over k here. It will cancel this one. So I will group all the terms involving phi on the left side. Now I have phi of k. Then k and z0, I'm going to put it in the origin now. Now I'm going to say that z0 explicitly. I'm going to say that z0 is equal to 0. Then I have the two-dimensional version of this potential. This is going to be multiplied by 1. And in the other side, if I move this thing to the left side, I have 2 pi alpha 2d and modulus of k. And this all multiplies phi. This is what I have for the right side. I have 2 pi of e over modulus of k. And finally, this is what I get. Phi two-dimensional depends on k in plane, only in the plane coordinates. Then I have 2 pi e over k multiplied by 1 plus 2 pi alpha d 2d k. What am I saying with this? What is the conclusion here? I can conclude that this thing here is playing the role, because if I had only 2 pi e over k, that would be simply the Fourier transform of a Coulomb interaction in 2 dimensions. And if this is a constant here, if this is just epsilon, then that is just a Coulomb interaction. But it's not just epsilon. This is epsilon of k. So what I'm saying is, in this approximation, what I'm saying is that epsilon, the effective epsilon k direction in the plane, it's no longer a constant. It's a linear function. 2 pi alpha 2d, and it depends on k like this. So it's a linear function of k. So instead of having a dielectric constant, you have a linear function, a dielectric function in k, in the k direction, right? So because of that's why you don't have a Coulomb interaction anymore. Coulomb interaction is if you have this as a constant, then you make a Fourier transform back and you get 1 over r. But now that's not what you have here. If you have a linear function here, when you make the Fourier transform back, you get a different potential, which is the one that normally people call it the Rytova-Keldysh potential, which is phi of rho. This is it's going to be something like e squared over 4 alpha 2d, the alpha 2d that you use it here, and then a combination of a Struve function, like that. Here you have r rho over rho 0, and a Neumann function of the of order 0, rho over rho 0, and this rho 0 is something that is like a screening length. That is just this number that you get here, 2 pi alpha 2d. That's this length here that multiplies the k, right? It has a unit of distance, right? So this is a screening length, and this is going to be what they call the Rytova-Keldysh potential. And this is what you get from this very simplistic approach here. But the problem is this, it cannot give you information if you have like in the bottom of the system like a substrate or a capping layer in the top of the system. If they have different epsilons, how does that thing enter this equation? So it's hard to predict what is the influence of the environment, of a real influence of this environment in the system. and I had some strong approximations here. What about the width of the slab? Where does the width of the slab enter? So this is all supposed to be, because I made a very strong assumption here, which is the fact that I know that something is induced in this system. This is where it enters. So the width of the slab and the epsilons, they should all enter this alpha 2D divergence of this polarization. This should all be, this should take into account all these things that I'm talking about, like the epsilons of the environment and the epsilon of the width of the slab. But okay, this is in a simplistic way, but I want to see exactly how this alpha 2D can connect to the width and the epsilons that I have in the system. So that's why now I'm going to go for a more sophisticated approach. Okay. Now let's assume that you have a slab that has some width. So let me draw it like this. So it has some width that I will call D, right? And then above this system, I will have an epsilon that I will call like a constant epsilon 3. And then below it, I will have some constant epsilon 1. But inside the slab, I have some constant epsilon that I'll call 2. And so this is a system that when you draw this is the z direction, right? Then if you plot epsilon of z, this is going to be something like, here is a function of z. I'll have this epsilon 1, let's say it's smaller than epsilon 2, and some epsilon 3. It can be the same as epsilon 1, for example, but it could be also something like that. And I'm going to draw it with the origin for z equal to 0. I'll put it in the middle here, okay? So then this point here and this point here, this will be like d over 2 and minus d over 2, to be something like that, okay? So then this function will be here in the middle, z is equal to 0. Here is this interface would be at z equal to d over 2. This interface will be at z equal to minus d over 2. So these are these numbers here, here and here. And this is the middle that I'll call z, and I'll put the charge exactly in the middle here, right? So I'll have this charge here, and this is going to be the charge that will generate the potential. So what I'm saying with that is that if I want to calculate a potential here at any point in the plane, and I'm calculating it at z equal to 0 and everything, so I would have to solve some kind of Poisson equation that would be, let's say that I would solve it piecewise, like in different pieces, different regions. So I will solve it for region 1, 2, and 3 separately, and then I will make boundary conditions for the continuity of the function of the potential and of the derivative of the potential. But let's first say that if I would solve it for region 2, then the solution is going to be something like, or the equation actually is going to be something like Laplacian of phi at that region would be something like, I will have a charge here, so I'll put it like E and this delta for the charge. And I'm now using these units where you have this 4 pi inside already the units here. And then I'll have this epsilon of 2. I'll put epsilon of 2 here. As I'm saying that I'm only in the region 2, then I don't need to worry about how epsilon changes for the moment, right? This is epsilon 2 only inside this region. And then once you solve the equation like that, I can take a Fourier transform of both sides, and then I will solve it for phi. It's going to be a phi of rho. It's going to be something like E over, if I want to talk about the electrostatic potential, then you'll have a E squared here, right? This would be E squared over 4 pi epsilon of 2, epsilon 0. I forgot to put an epsilon 0 here indeed. And I would have a solution that would be something like an integral over some k, and then Bessel function, because this is circularly symmetric, of whole multiplied by k, and this is this in-plane coordinate here. And here I will have some constants, a of k. I'm going to call it a of the region 2 of k, e to the kz, and b of region 2, it may depend on k, e to the minus kz. And as I have a non-homogeneous function, non-homogeneous equation here, then I will have to add also another component here that would be exponential of minus k and the modulus of the z direction here. This is the solution for region 2. And if I want the solutions for regions 1 or 3, I'll put, let's say, the solution for region 1. So just a quick explanation for what I'm doing here. Why do I have these exponentials here? Actually, this is not so complicated to solve. If you make a Fourier transform only in the, let me put it very quickly here. If I have a Fourier transform only in the in-plane coordinates here, then I'm using a Hankel function. It's a Fourier Bessel function, right? So Fourier Bessel transform, I mean. So a Hankel transform, which is a Fourier Bessel transform. So then I will have, for in-plane coordinates, I will have something like a k squared and phi, and I'll have also for the z direction something like dz squared of phi, and this is going to be 0. And then in the end I have something like a derivative of z, and this is actually a minus here. So the derivative in z should be proportional to k squared over phi. And then if I want to find a function in z direction that solves this equation, it can be either an exponential of kz or an exponential of minus kz. And that's why I chose these two things here. But in the end, I have to take a Fourier transform back to real space in the in-plane coordinates, and that's why I have this integral in the dk and with the Bessel function here, as I'm using this Hankel transform. So that's why the solution should look like that. Then in region 1, I would have also some solution like that, but as I don't have a homogeneous function, the homogeneous equation for region 1, then I could just write this thing like e squared over 4 pi epsilon 2 epsilon 0, and the integral would be more or less the same. Let me put the variable here already. Then I have j0 k whole, but then there's something different here, which is in region 1 I have a1 of k e to the kz, and notice that I cannot have in region 1, which is the bottom of the system here, it goes to minus infinite. So I cannot have a b1 here, because otherwise it will diverge. So, and I also don't have this exponential here, because it's a homogeneous equation. There's no charge in region 1. So I can just write it like that. So for region 3, this is going to be something similar to that too. So for region 3, I have phi of whole. It's going to be e squared over 4 pi epsilon 2 epsilon 0, the integral in dk in the plane, j0 k whole. And for the z direction, the solution is, I don't have the exponential again, this is exponential of the modulus, and because there's no charge in that region, and I cannot have exponentially increasing solution. I can only have exponentially decreasing solution, otherwise the solution will diverge, the potential will diverge in z going to e plus infinite, right? So the only thing I can have here is a b3 of k, which multiplies exponential of minus kz, right? So these are the three solutions that I have, and what I need to do now is to use those solutions in the boundary conditions, right? So one thing that I need to have is that the solution for the first interface is minus d over 2. So exactly at this interface, minus d over 2, then I will have the solution for 1, which is a1 of k, right? This should be multiplied by exponential of minus k d over 2, and this exponential here is positive, so there is this is indeed the original exponential here is with a positive argument, so the z will be minus d over 2, so it's written like this. So this is what I have in the before the interface. It has to be the same as what I have after the interface. That would be a2 of k and exponential of minus k d over 2 and b2 of k. Then here I would change the sign, and then now exponential of minus k and the modulus, that would be d over 2, right? Now there is another boundary condition, which is the derivative of these expressions should also match. And notice that the equation is like divergence of epsilon gradient of phi. So this is what I have in Poisson equation. So what has to be continuous is this thing here. So my continuity equation should look like this. The continuity for the derivative, right? Epsilon 1 derivative of phi in z for z smaller than d minus d over 2 has to be epsilon 2 derivative of z for phi for a z larger than minus d over 2, but approaching this value, right? So when they approach that, I will have two different derivatives, but when I multiply by the epsilons, then I need to get the same result. Then what I have as an equation here would be like this k and a1 exponential of something like that, and also this k a2. Then here I'll have minus k and b2 exponential of k d over 2, and the derivative here, remember that this exponential is an exponential of the modulus of z. So this is going to be a increasing function. It has to be like a plus k exponential of minus k d over 2, right? And keep in mind that I didn't put the epsilons here, so I'll have an epsilon 1, epsilon 2, and epsilon 2, right? Okay, now I can divide everything by k, right? And this is going to be my second boundary condition. So if you go on with this calculation you make this boundary condition now at z equal to d over 2, that's the second interface, then you get another pair of equations. I'm going to skip this thing, you can do it yourself there. You can rewrite, I'm just going to rewrite the set of equations. Remember that I have only four variables here, a1, a2, b2, b3. These are the variables that I have. So what I have in the right hand side of this system of equations would be, for this first equation, for example, then I have just exponential of minus d k over 2, right? So for the second one, I can already write it here. It's e to the minus k d over 2 epsilon 2. Then when you do it with the other equations, you will find something like minus e to the minus d k over 2. And for the fourth component here, you will find epsilon 2 e to the minus k d over 2 again. And then for the matrix here, I can already put some of the values here. The first one, this is what multiplies a1 in the first equation. So this is e minus k d over 2. Then the next term, this is what multiplies a2, but it will be in the left side, so it's minus exponential of minus k d over 2. This one is what multiplies b2, so it's another exponential, and it's also with a minus sign, so minus e k this is positive exponential kd over 2, and there's nothing multiplying b3, and that's why I have a 0 here. So next line of the matrix should be, in this one I have epsilon 1 multiplying e minus kd over 2, then I have epsilon 2 multiplying e minus kd over 2, but then I had to pass it to the other side, so there is a minus here. So this other one will be a plus epsilon 2 e to the kd over 2, and then there is nothing else multiplying b3, and that's why the equation will be like that. And then if you go on with these equations, we will find a set of 4 equations, then you will have a matrix like that. I'm going to write the matrix here just for the sake of to make it complete. So the next 2 equations, they cannot have a1 component, so because they are at the second interface, the interface at d over 2, which means that I have only a condition for a2, b2 and b3 components. Then I'll have only 0 here and 0 here, and then what multiplies these things here should be one thing that multiply a2. The first thing should be exponential of kd over 2, right? This is what multiplies a2. Then there will be something else multiplying b2, which should be exponential of minus kd over 2. Something that multiplies b3, this is going to be on the right side of the equation, so I'll have to put it on the left hand side of the equation. It's going to become minus exponential of k d over 2, and it's a decreasing function, so it's a negative here. So this is what you get. And the next line is for the derivative. So when you take the derivatives, there will be one epsilon here, which should be epsilon 2. The exponential should be kd over 2. Then there will be also an epsilon 2, but now when you derive, you get a minus sign, exponential of minus kd over 2, and then the term that derives this b3, when you derive, you get a minus sign. When you put it on the left hand side of the equation, it will be positive, and now you have epsilon 3 exponential of minus kd over 2, and that's the matrix that you get in the end. Now if you want to solve this system of equation, remember that what are we looking for? We are looking for a2 and b2, so that I can construct this thing. Because let's think a little bit what do we have here. If I have this epsilon 2 multiplying this thing here, this whole thing, this is what is multiplying my Fourier transform, right? So this Fourier transform, if you think about it, there should be a k here, but that should be k dk, because it's like in polar coordinates, right? But the thing is, I have k dk, but in the bottom I should also have a k multiplied by some epsilon. So that's why I didn't put the k here. So I don't need to put this thing here, and then okay. So whatever I find in the rest of this equation here, whatever I find for this epsilon 2 multiplied by this thing, this is the effective epsilon. This has to be what I found here, right? At some point I need to find this. So epsilon 2 multiplied by this thing should give me exactly something that at least at some limit should look like this one that I just found here, because this one shouldn't be wrong, right? So then what I need to do is to find something like an epsilon, this effective epsilon that I'm looking for, which is epsilon of k, should be something like epsilon 2 multiplied by 1 over a2 of k, and then as I'm doing it at z equal to 0, then I have only a2 of k plus b2 of k plus 1, because the exponentials will go to 1, because I'm at z equal to 0, right? So if I just find this a2 and b2, then I'm done. I can just like add to 1 and make the inverse and so on, and then I should find that expression somehow. So I'm not going to make this thing here because this is a four equations. This is a system of four equations with four variables, so it's not very simple to calculate. But you can do it with Mathematica. It's not going to be so hard to do with Mathematica. Then in the end, the solution that you get, it's something that looks like epsilon is the epsilon of k is going to be epsilon 2 multiplied by, if you do it like, at least when I did it in Mathematica, I got it straight like this when you use this full simplify function of Mathematica. It's 1 plus epsilon 1 minus epsilon 2, then e to dk, then epsilon 1 plus epsilon 2 minus epsilon 1 minus epsilon 2. And then you add another term, which is epsilon 3 minus epsilon 2, e to dk epsilon 3 plus epsilon 2, and minus epsilon 3 minus epsilon 2. This is what you get straight from Mathematica. If you put that matrix that I put there, and you simply calculate the just to give you a little bit of information how I did it in Mathematica, I call this thing a vector, let's say x, and then I call this vector b, not to confuse with the other b, let's use another letter then. I call this thing, let's say, b bar, and this thing I call it matrix m bar, something like that. And then I found x is the inverse of m bar multiplied by b bar, and then if I want a2 and b2, I just get the second component of this x that I just calculated, and then the third component of this x. Okay, so this is how I did it. After some math, you will end up with some expression here, which should be something like this is kind of exhausting to do this kind of calculation, but if you do all these calculations here, you add these things and multiply by epsilon 2 and so on, in the end you will get something like epsilon 1 plus epsilon 3 plus 1 minus epsilon 1 epsilon 3 over epsilon 2 squared, epsilon 2 hyperbolic tangent of k multiplied by d, and in the bottom here you have 1 plus epsilon 1 epsilon 3 epsilon 2 squared, and 1 minus epsilon 1 epsilon 3 over epsilon 2 squared, and here is this hyperbolic second of k multiplied by d, and epsilon 1 plus epsilon 3 over epsilon 2 hyperbolic tangent again. Okay, so this expression doesn't look much like this one, right? Doesn't look much like the one that I just found here. But actually, when you plot this thing, this epsilon, as a function of k, then what you get is something like this. It starts like this, and then it converges to some number. So actually, the fact that it converges to some number, it will converge to epsilon 2 actually. And why is that? That's because if you have a system that is a very large slab, then you have this slope here to become much sharper, and then you have just a constant epsilon 2, and that's it. And that's why if you have a very large slab, it will look like a 3D system. And if it is a 3D system, what you have is a constant for this thing, and then you have a dielectric constant, not a function, and then you have Coulomb interaction. But this is not a 3D system, so the 3D approximation that I'm talking about here is going to be this one, that's the green one. But now, if you take D as a very thin slab, and you say that you need to do these two things, I'm going to demonstrate later on, but you need to say that the slab is very thin, and you need to say that epsilon 1 and epsilon 3 are much smaller than epsilon 2. Then you have this thing here will dominate, and you will have a linear function, and that's the linear function that I have here. So this is what I should look for a way to say that this is the dominant part of my function, because qualitatively it will look like this, but maybe at some approximation I should say that this region here is the most important one. And this is actually, when you look at Rytova and Keldysh's papers, in this paper here and this one, you would see that, at least in this one for sure, in the Rytova paper, I don't remember right now, but maybe you could look there. But in Keldysh paper for sure he made this approximation. So to find this linear expression, and eventually to find this kind of expression in real space, there was an approximation which is epsilon 1 and epsilon 3 are much smaller than epsilon 2, which should be true if you have a material that screens a lot and it is, let's say, surrounded by vacuum only, where epsilon is only 1, right? Maybe if you put, let's say, a silicon in vacuum, then you have 10 for epsilon 2, but you have only 1 for epsilon 1 and epsilon 3. So it's 1 order of magnitude larger. Then it could be a good approximation. So this is what I'm doing, and also I'm doing that KD is much smaller than 1. So if I do it like that, the hyperbolic tangents, they are going to become simply KD, then this one is simply KD, this one will become 0, right? But I'm also saying that I have this epsilon 2, it's much larger than epsilon 1 and 3, so this thing will also look like 0, this thing will look like 0, this thing will look like 0. Actually, the second is going to be 1, right? Sorry about that. The second is going to be 1, second. Hyperbolic second is going to be 1. Then there will be 1 here, but this one is 0, because epsilon 2 is larger than epsilon 1, and epsilon 2 is larger than epsilon 3, then I will put this to 0. Then in the end, the red approximation here, which is the linear one, ends up as being epsilon 1 plus epsilon 3 over, then this 1 here with the 1 here, it's going to be 2 plus epsilon 2 dk. And now I'm going to rewrite it like epsilon 1 plus epsilon 3 over 2 multiplied by 1 plus epsilon 2 d over epsilon 1 plus epsilon 3 and k here. Now there should be a 2 here. So, well, then in the end what I'm saying is, finally, what I'm saying is this thing here is what plays the role of the 1 plus 2 pi alpha 2d k in my previous calculation, which means that this thing here plays the role of 2 pi alpha 2d here, and that's the Rytova-Keldysh approximation. So that's an approximation where you have epsilon 2 much larger than these things and kd much smaller than 1. Then this expression that I just found here, the expression that gives me the black curve there, this expression will be approximated as this linear function, and then everything else happens like this. My epsilon in that approximation will look like a linear function, and then you take a Fourier transform back. For Fourier, you apply this thing here, right? You take a Fourier transform back, you will find exactly these Struve and Bessel functions for the potential, right? But if you don't have these conditions matched, then you shouldn't be able to use Rytova-Keldysh approximation, which means that, for example, if you have some slab that is immersed in a high K dielectrics or something, then you need to have a function, at least as a better approximation, it should be something like this, like the black line here, because it would not look like a linear function like in Keldysh approximation, or it would not also look like the constant here. So you will have a epsilon 1 and epsilon 3 that will enter the equation in the way I just wrote here. So just keep in mind that these red crosses that I draw here is only if you say that these approximations are valid. So So if these approximations are valid, then you have this red crosses here. I just like can cancel out many of the terms and approximate some stuff, and in the end I get a linear epsilon as in Rytova-Keldysh approximation. But otherwise, this is the potential, and it looks linear in the beginning for the first values of k, and then it becomes constant in the end. And by the way, this thing here, it converges to epsilon 1 plus epsilon 3 over 2. Right, so this thing will converge to this, and this one will converge to epsilon 2 for k too large, and that's it.